So far we've talked a lot about what a differential equation is, how it can be used to model the real world, and what it means to have a solution. We haven't talked at all about how do you actually find the solutions, or at least how do you find a formula for the solutions. Partly that's because formulas are overrated. It's really more important to have a qualitative sense of a differential equation than to actually find a formula. And partly because we just hadn't gotten around to it yet. Now we're going to get around to it. So we're going to start talking about how to solve a differential equation, and we're going to deal with the two simplest cases in this video. And remember, we're dealing with first order differential equations, so dy dx is some function of x and y, and typically we think of y as some physical quantity that's changing with time, and x represents time. Sometimes we call it t, sometimes we call it x, doesn't really matter. And the very first special case is where the rate of change only depends on time and it doesn't depend on the value of the quantity. So for example, you might have dy dx equals 2x. There's no y in that equation. The right-hand side only involves x. It doesn't involve y. Now that's pretty easy, and we've done a whole lot of that in our methods of integration section. I mean, all this is saying is the derivative of y is 2x. So dy is 2x dx. We integrate both sides, and we say, oh, y is the antiderivative of 2x, which means that y is x squared plus a constant. It could be that y is x squared. That's a solution. Or it could be that y is x squared plus 1. That's also a solution. Or x squared minus 1. That's also a solution. Or x squared minus 2. That's also a solution. You have a whole family of solutions, but they only differ by adding this one constant. You know one solution, add a constant, you've got all the others. So how do you actually get that constant? You plug in your initial conditions. If someone tells you that when x equals 1, y equals 3, then you plug that in. Y equals x squared plus c. You get the c equals 2. And that allows you to predict the value of y for any other value of x. Like when x is 5, well, x squared plus 2 is 27. So there you go. From the fact that at time 1 you were at 2, you predict that at time 5 you're at 27. Okay, that's the simplest kind. The next simplest kind is where f of xy does depend on y, but it doesn't depend on x. If we think of x as being the time, it means the rules of the game, the differential equation is telling us how something is changing. The rules of the game don't change. The function changes, but the rules don't. Now, dy dx equals f of y. You can't just integrate that, but you can use the chain rule. The chain rule tells you that dx dy is the reciprocal of dy dx. So dx dy is 1 over f of y. And now we have the derivative of x that doesn't depend on x. That's case 1. It's case 1 where we're solving for x in terms of y instead of y in terms of x, but it's case 1. We flipped the roles of x and y, and we know how to do this. We get dx is equal to dy over f of y, and then we integrate both sides. The integral of dx is x, and the integral of dy over f of y, well, that's an integral. We have to figure out how to do the integral, but it's just an integral. You don't have to use fancy methods of solving differential equations. You just have to be able to do an integral. That integral will involve an arbitrary constant, so you get a whole family of solutions. And then that gives you x in terms of y. What you really wanted was y in terms of x. You use your inverse functions to invert this, to solve for y in terms of x. So, for example, let's look at the differential equation dy dx equals 3y. So that means dx dy is 1 over 3y. So dx is dy over 3y, and we integrate both sides, and we get x is 1/3 natural log of absolute value of y plus a constant. Now really I should have said x plus a constant is 1/3 natural log of y plus some other constant. Because when we integrate here, we have a constant of integration. We integrate here, we have a constant of integration. But we can always just subtract c1 from both sides, and one constant minus another constant is just a constant. So whenever you have integrals on both sides, you don't need two constants of integration. You only need one. So I'm just going to call that one constant of integration c. Now, you solve for natural log of y, and you get that 3x plus a constant, and c prime is negative 3 times c. It's just another constant. You exponentiate both sides, and you get the absolute value of y is e to the 3x times e to the c prime. That means that y is plus or minus e to the c prime times e to the 3x. And this is just a constant. Take a constant, exponentiate it, take plus or minus it, it's still constant. Give it a name, we'll call it a, and there we have our solution. Y is a e to the 3x, where a is any constant. So that's a typical application of this second simplest kind of differential equation. In the next lecture, we'll talk about more complicated differential equations.